Hi, this is Miss Litton, and this is my wonderful Period 3 APBio class. Say hi.
Hi.
And they are ready and they are engaged for today. And we are basically going to review the nephron structure and function, and then we'll pick up where we left off in the notes about the kidney and homeostasis. Oh, you can't see what I'm seeing. So the first thing I want you to remember are, what are the three parts of the kidney? What are the three parts of the kidney? Do you remember this?
Oh, it's the cortex?
Yeah, the cortex, medulla, and the pelvis. Okay, let me back it up just one more second here. When we look at our urinary system, we see we have two kidneys. What is sitting on top of the kidneys?
The gland.
What is that gland? Adrenal gland. Good. Adrenal gland sits on top of the kidneys. What's descending out of the kidneys? Yeah, I heard it somewhere. Ureters. The ureters. How many vessels are actually connected to the kidneys? Three. What are they? Renal artery, renal vein, and ureters, right? Two blood, one pee, right? And then the ureters come down, they join at the bladder, and then what is the name of the tube that exits the bladder? Urethra. Perfect. Okay, if we cut the kidneys in half, we have a cortex, medulla, and pelvis. The functional unit of the kidney is called the nephron. About how many do we have per kidney? Over 1 million. Okay. What is the functional unit of your lungs? Alveoli. Good. So it's in that same, right? Okay, so when we look at a cross-section of the kidney and you look at the nephron, there are different, distinct things that happen all along that structure, and you want to be comfortable with that. Okay? So I'm going to do it simply at first, and I'm going to give you some chance, opportunity for you to practice this as well. Remember, this only works, what we're going to be talking about, because there are not one but two sets of capillaries. The first set of capillaries is called a glomerulus. It's a ball of capillaries, and it sits in the glomerular capsule. What's another name for the glomerular capsule? Bowman's capsule. Good. The second set of capillaries goes around the rest of the nephron, and they're called peritubular capillaries. And what we see here when we're looking at this nephron is that here they have the glomerular capsule around it and then exposed. That at this first set of capillaries, everything comes out. What was the example I said to think about, the analogy? Purse. Dump everything out of the purse, right? But if we threw everything like that away, that would be really bad, right? So we have to recover. What's the number one thing we have to recover? Water. Okay? So we have multiple opportunities to recover that water, but we know you can never pump water, though I asked that question many times, and sometimes you still tell me you can. But you can never pump water, but I can motivate water. How do I motivate water? Make it a hypertonic environment, and then water will follow. Water must flow from the hypo into the hypertonic environment. So everything gets dumped out. It goes in that glomerular capsule. And then as you pass through this tube, this is the proximal convoluted tubule, then the descending loop of Henle, ascending loop, distal convoluted tubule, and the collecting duct. And there could be several other nephrons attached to that one collecting duct. When you get right away to the proximal convoluted tubule, about 67% or so of the salt gets pumped out. And when it gets pumped out of that P tube, it's really just called filtrate then. Okay, but when that salt gets pumped out, who's going to want to follow it? Water. So you get a whole bunch of water right there that recovers. Okay, the same thing happens at the distal convoluted tubule. Salt gets pumped, and water follows. Gets returned to your ultimately to your cardiovascular system. But something else happens at the distal convoluted tubule. Do you remember what that is? Oh, secretion. Good job. This is where things that aren't in the P tube and the filtrate, you want it to be in there from your blood, so you will actively transport it in there. It could be creatinine, some drugs or things that you want to make sure get into the P tube and then you get rid of it out of your body. That's where you do that primarily. You actively transport things into the tube so that you'll urinate it out. So these two have things in common. The proximal and distal convoluted tubule have something in common. They both pump salt, and who follows? Water. Okay? But at the distal convoluted tubule, something goes in. What is that? Waste, right? And what's that called? Tubular secretion. So now, at this point, we can address all three words we need to know about the kidney. There's filtration, but the filtration part is always associated with the glomerulus. So it's called glomerular filtration. Okay, and this is happening right here, right? At each of the glomeruli, you're doing glomerular filtration. It would be like if you had cooked a bunch of pasta, okay? And when you're done cooking the pasta, you want to get rid of the water and just have the noodles, right? So you have a strainer. Think of it like that, okay? And so you're straining everything out. The only part that remains inside your blood are the formed elements. What are the formed elements? Platelets, red blood cells, white blood cells, and any large proteins that can't get out, that would normally pass out. Everything else in the plasma, it's going out. What's dissolved in the plasma? Gases. Well, it's made out of water for sure, but gases, proteins, nutrients, nitrogenous waste, vitamins and hormones. Perfect. All of that's going out there. Okay? So we have a place here, salt, water follows, salt, water follows. On which way does water roll? Uphill, downhill? Downhill. Okay? On your two downhill portions of the nephron, water's going to come out again. And that would be here at the descending loop, okay, and also at the collecting duct. So your two downs, that's water's going to come out, okay? Why is it going to come out? It's all because of the ascending loop. Because the ascending loop that goes up, actively and passively, salt comes out, but who can't follow? Water. So the ascending loop sets up the descending loop and the collecting duct. You know what I'm thinking right now? I'm thinking countercurrent. Okay? So then when I think countercurrent, what comes to mind? I'm thinking fissules, exactly. And by going at two different directions like that, that allows you, just in the gills, to increase the amount of oxygen that the gills can pick up, right, out of the water, because it's always facilitating the transfer. The gradient is always facilitating the transfer. Same thing here. By setting up this concentration gradient, and because water can't fall out of the ascending, it makes it so the descending, moving opposite direction here, the water wants to get recovered. It wants to go out into that hypertonic environment. So that's key. Okay? Then on the collecting duct, water does come out, but at this point the urea that's been in the tube the whole time, right? It got put in at the glomerulus. It's been traveling. I'm urea. It's been in there the whole time. Some of it starts to diffuse back out a little bit just because it's so concentrated. Okay, so that's one pass at it. Let's take another look at it. And when I say here, when I gave you the analogy of the purse, where would this be occurring? At the glomerulus. What do you call it? Glomerular filtration. Okay? Then when you're picking things back up and putting it back into your purse, what would that be analogous to? Tubular reabsorption. Tubular reabsorption. Okay? If there was something in my purse that I had to scrape out, like a piece of gum stuck inside of it, and I had to work to get that out of my purse and get it thrown away in the trash, that would be tubular secretion. Where does that happen? Distal convoluted tubule. Distal convoluted tubule. So what gets left over here? We don't pee powder. At least I don't. You don't go poof, right? So there's still water, right? There's still water in that urine. But the amount of water in your urine is going to be highly dependent on what your body needs in order to maintain homeostasis. So we're going to talk about some of the things that regulate how much water remains in there. But before we do, take a look at this one. And youngest bio buddy, you take the first swipe at it. This is a simplified nephron. Okay? Talk about what's happening at each step. Go ahead, youngest bio buddy.
Yeah, and then it goes. There are no globular capillaries, and the bones have
Now, can you do me a favor? I gave you a summary at the end of these notes. Kind of scroll down to that summary at the end. Okay? And go to number 3. Do you see number 3? The nephron is organized for stepwise processing in blood filtrate. Structure and function, baby. Okay, so number 1 is what? Filtration. Where is that happening? At the glomerulus, everything out. Step 2 is? And that's coming out of the nephron and into the peritubular capillaries, right? Tubular reabsorption. Step 3 is what? Where is that happening? Distal convoluted tubules primarily. And then step 4 is excretion, right? That's urinating out. And is that represented here as well?
Yes.
Okay, so this is a real basic one. Any questions on this part right here? Yes?
Is there 2 different pathways that the blood can go through?
One pathway that the blood, remember the blood's going to always flow in one direction, right? So it's going to go from the heart, right, into the aorta, and then branching arteries, and then into the renal artery, and then it goes into the afferent arteriole, the glomerulus, the efferent arteriole, the peritubular capillaries, venule vein, renal vein, and back to the heart. Okay, and I'm going to show you a picture that shows the blood there. This was just simplified, but it's all in one pathway. But the cool part is 2 capillaries. Where else have we seen 2 capillaries again? Between the and the what? Small intestines and the liver, and it's called the hepatic portal vein. Yeah, between them, and it's the system. Yeah. Okay, so now, let's see, youngest bio buddy. You took a swipe at that, right? So now, oldest bio buddy. Before I let you loose, let me review one more time with you because you're going to be doing blood and filtrate pathway, okay? So let's take a look at our structures. We have a branch off the renal artery, right? Not visible. A branch off the renal artery. Then it goes afferent arteriole, then the glomerulus, and then an efferent. So afferent, then efferent, okay, going away. So maybe exit. Or A comes before E, however you want to remember that. Okay, afferent before efferent. This right here, the glomerulus, is a ball of capillaries, and everything's coming what? Out. Okay, then it's moving through here. What is all of this surrounding it? It's called the, it starts with a P, peritubular capillaries. Good. What is happening right here at the proximal convoluted tubules? Okay, salt and what? Yeah, so salt's getting pumped and water is following. Yes? Now we're going to go down the descending loop. What's happening here? Just water. Okay? Up the ascending, just salt. Then the distal convoluted tubule, what's happening there? Salt and water and tubular secretion. Perfect. And then we go down the collecting duct, and what's happening? Water due to the ascending, right? And a little bit of urea gets back in. Okay? Now I want you to look at something when you look at the structure. Oh, that's super awesome. Yeah, okay. All right. If you look here, oh, this isn't the picture. Never mind, not this picture. It'll come up in a second. Okay, oldest bio buddy, this is you. Okay? Please explain the processes of the nephron. Go ahead. I yell in your own words.
Distal convoluted tubule, same thing happens except waste is also
Okay. So look at the words that I used right here. What's happening right here? Can you read that? It's blue, sorry. Glomerular filtration. So glomerular filtration is happening here. Everything that you see here would be under the umbrella of tubular reabsorption. And then right here where the white arrow is, that's where tubular secretion is going on, right? And then This collecting duct is going to lead to the medulla and the pelvis and the ureters and the bladder and urethra, and that would be called excretion. You good with that part? Okay, another thing I want you to see is look at the walls of the nephron. Okay, look at the walls of the nephron. And if you look up here, do you see how it's just, it's just outlined right here, and you can see water coming out of here. There's the descending loop. Here's the ascending loop. Here's the collecting duct. Do you see anything different about these three walls? See on the ascending one, how it's a little bit darker? That's trying to show and represent for you that it is impermeable to water. Think about it. Everywhere you go, water can move, right? So that's kind of a rarity to prevent water from moving. It's a small polar molecule. That thing can move, okay? But here at the ascending loop, and that's critical, because the ascending loop being impermeable to water sets up the descending loop and the collecting duct, right? So if I put my hands up here and I'm a nephron, look, I'm a nephron, okay? Up here is salt and water, okay? Ascending is only salt. Descending and collecting duct are water, and here a little bit of urea. Perfect, okay? And then up here, what would be happening up here? Tubular secretion. Right? Do you feel comfortable? Ask your body buddy, how comfortable are you feeling? Are there any things where you're a little shadowlands, a little concerned? Yeah. Okay. So, let's see how you do on, I think we might have asked these questions before. We were, okay, we need to think of something. You can be different if you want to. But we did this last class, is movie theme. So you can pick a character, can't do a whole line, but try to come up with some movie theme name, like Deadpool or something like that. Wait, Emoji Movie 2? Has there been Emoji Movie 1?
It's Emoji Movie 2017.
Oh, I'm all. Have there already been one before that? Build a wall. Very good. Trump is in the house. Which I don't appreciate at all. Just letting you know in case you're wondering.
Zach Nephron. That's a good one. Zach Nephron for Zach
No.
Oh my gosh. Did you see that last night?
I predicted his filtration is in the...
Make them think. I love the movie The Big Short. Who has seen that?
Oh, I love that movie.
It's a good movie. Hermione. Am I saying her name right? I used to call her, when I first read it, Hermione.
That's what I said. Yeah. I got made fun of in like elementary school for sure.
I'm sorry.
If not the only reason.
Me too.
I don't watch any of the movies. I just read the books.
I know, I hadn't seen it. I just read the books. All right, I cannot wait. Okay, so almost all of you got this. A blank artery exits. Which one exits? The efferent. Afferent goes in, efferent exits. Check your bio buddy's screen. Did they get that one right, or do you need to ring a little shame bell for them? Need a little shame? Oh. How many times will we go over this? I think I've actually said it maybe 5 times. I'm going to go with 5. And 5 people missed it. Welcome. Welcome to class.
6 people.
Oh, 6. Okay. I just assumed that was somebody who wanted to elongate it on a different name, you know. But filtration is associated with the glomerular capsule. 5 of you said all of these. No. Let's review for those 5 or 6. What happens at the distal convoluted tubule? Tubular secretion and what else? Reabsorption of salt and then water. Okay, and collecting duct, only water and a little bit of urea. And yeah, no. Check your bio buddy's screen. Shame bell, need a little shame? Throw a little shade if they need it. Okay. So you're right. Water is reabsorbed from the collecting duct, but it's also found in the glomerular filtrate, it's reabsorbed from the nephron, and it's in the urine. 2 of you struggled on that, potentially 4 of you struggled on that. Can you check your bio buddy's screen and help them? Say something positive or guide them right now. Either say something positive or guide them. All right. Before I say another word, could the youngest bio buddy go first and then the oldest bio buddy finish the sentence? The kidney helps with homeostasis by, and youngest will go first and then oldest bio buddy. Go ahead. Could you not see a question? Homeostasis is maintained by many different systems in the body. Please pick 2 of the following and describe their role in maintaining homeostasis. Do you see what I'm saying? Those are the kinds of things that you would ask, where you would have to give an example. What would happen under these conditions? Maybe they would give you, you know, where homeostasis is thrown out, off. What systems could be used to combat that, you know, disruption, blah, blah, blah. You would want to come up with ways, okay, to apply it. So here, okay, on the functions of the urinary system, we have already talked about metabolic waste, and that was in the ed puzzle I had you do. Remember, urea and uric acid were discussed in those 2. Creatinine comes up, and creatinine is a way, creatine phosphate stores phosphate for us in our muscles, so it can easily be given to ADP in order to make it back into ATP. Good. So a byproduct of that metabolic reaction is creatine or creatinine, and we get rid of those. And you know how we get rid of those? By actively transporting them out of our blood and into the filtrate. Where will that happen? At the distal convoluted tubule, exactly. Okay. We have talked about water and salt balance, okay, already, and we'll talk about acid, base, and hormones as well. So let's talk first here. Job 1, getting rid of the metabolic waste. There they are. And here they are in a beautifully colored fade to darker yellow slide that I've made there for you. So go to excretion of metabolic waste. Urea is from the breakdown of what? This is me praying. Yes, amino acids. Terrifying. Urea is from the breakdown of amino acids. Just so you know, or review, do you know who does that for you? The liver. In the process of breaking down that amino acid, if you're not going to change it into a different amino acid that your body needs, if you aren't going to do that, you have to cut off that ammonia, the NH3 part, and that's called deamination, and that's done by your liver. Okay. Creatinine is from creatine phosphate, and that's energy in muscles. That's how you store energy in muscles. And uric acid is formed from the breakdown of purines, and I'm going to talk to you a little bit more about that in a momento, and gout. So take a look at this little diagram. Here is man without a real face or a penis. And he's going to eat this steak. What is the steak full of? Proteins. In his mouth, what kind of digestion will take place?
Or mechanical.
Mechanical, using what? Teeth. And that teeth will digest what? All food. Okay? Is there anything chemically digested in his mouth?
Yeah,
Starch, carbohydrates. Good. When he swallows it, what's going to make sure that this steak doesn't go into his lungs and his trachea? Epiglottis. What is going to move this, obviously in smaller pieces, through his esophagus? What is that called? The cilia or your trachea? Starts with a P. Peristalsis. Good. Okay? It now moves into your stomach. Okay? What's going to happen in the stomach? Pretend the steak's in there. Chemical digestion and also mechanical digestion, the churning, right? So the stomach and the small intestines are going to contribute to the digestion down into what's the monomer? Amino acids. Okay? That is going to get picked up, right? At the capillaries. What do you call the folds inside the capillaries? Microvilli, right? Which increases, oh, where did I say?
Capillaries. You said the
Capillaries, the folds in the capillaries? That's unique. Folds in the small intestines? Yes. Yes. Which increases what?
surface area.
And then those capillaries within the folds, right, are going to take that blood, we've already talked about it, and shunt it to the liver. Okay? And there at the liver, that blood that comes, okay, the liver will take the excess amino acids and convert them to other things. But the first step in that is deamination, removing that NH3 group. That NH3 will be converted from ammonia to a less toxic substance called urea, but that'll take some energy, right? Okay. So, and it'll take, the liver will take that urea and put it back into the blood. What's the name of the vessel that's going to leave the liver? Not renal, because that's the kidney. Hepatic vein, right? Not the portal vein, okay? Portal vein is between the intestines and the liver, okay? There's a hepatic artery and a hepatic vein that go to and from the liver itself. So it's going to leave the hepatic vein. It's going to go back to your heart, out to your lungs, back to your heart, and then back out to your body again. If some of that blood then goes to the kidney, what's going to happen in the kidney? What's going to happen in the kidney? The kidney is going to what? Filter out that urea, right? Where does glomerular filtration take place? At the glomerulus, because I said it in the name, right? It's going to go through all the tubes, and then it's going to get stored in the bladder until you pee it out. Fire pee. I made fire pee. I couldn't find urine. Okay, so did I tell you what I did here? There was a guy it was a picture of a guy cleaning his driveway, back when you could clean a driveway with a hose, and the water was splashing. I captured it, I outlined it, and then I used several different colors of yellow and orange to create that fire pea right there. I think he has an STD. Okay, but anyway, that's how it moves through. All right. Okay. Now, so that is one of your 3 nitrogenous wastes, right? The primary nitrogenous waste is urea. Okay? But there are other nitrogenous wastes as well. We're going to come to that. But you could also have creatine or creatinine, and this is from the metabolic breakdown of creatine phosphate. In case you were wondering what their structure was, it looks like this. Okay? You're not going to need to know that, but I just wanted to show the difference between creatinine and creatine. Okay, so there it is. All right, and so on your notes we had creatine, and then your third one was uric acid. Now, uric acid, right, you can get what's called gout from having too much uric acid, and that's if you have foods, eat a lot of foods with purines in them, and these are the foods with purines in them: heart, herring, mussel, yeast, smelt, sardines, sweetbreads. I don't know how much of that you eat. Anything on here you would eat though? Bacon, I would say, is pretty common, except maybe not. Yes?
So why do babies get gout?
Babies don't usually get gout. I think you're thinking about something else. Jaundice. And that's because their liver is not up to and functioning very well. And so what you can help with that process is putting them in the light, or they are in an incubator that has light. Yeah, different. Yeah, babies won't get gout. But look at what, so those are the foods. Bacon, I love salmon, and it's good for you. But if you eat veal, mutton, grouse, anchovies, partridge, I'm always eating partridge. But you're more likely to have gout if you have family members with the disease, if you are a man, if you're an overweight man who drinks too much alcohol. Wow. Overweight man that drinks too much alcohol and eats too much. Just think about a man who's kind of got a beer belly and likes bacon, okay? That's going to lend yourself to gout, okay?
Okay, this up without the beer. Oh,
okay. Yeah. All right. So uric acid formed from the breakdown of purines, nucleotides. Gout is too many uric acids. Gout is too many uric acids. It precipitates out as crystals and collects painfully in the joints. Too many uric acids. It collects painfully. It precipitates out as crystals and collects painfully in the joints. Precipitates out. Think about that. What do we know about uric acid? There are animals that make uric acid. That is their nitrogenous waste. They take the ammonia, convert it to urea, and then uric acid. Why?
Because they don't have access to water.
They don't have excess water, and so they'll store it. It precipitates out. Birds, right? Because they can't afford to have copious amounts of urine when you're inside a shell and developing, right? You would drown in your own urine. So it precipitates out, and it happens in us. If we have too much and our body can't deal with it, it becomes a crystallized little salt in your joints and then very painful. Okay, next. There is a strong connection. Look, see, that's super cute.
Hello, Kitty.
Hello, kidney.
Oh my God.
That's super cute. I like it so much. Okay, now there is a strong, strong connection between salt and your blood pressure. Okay, youngest bio buddy, tell them the connection between salt and blood pressure. Go.
Oh, okay. More salt, more water, more pressure. That took me a while to stick around.
So, if this was your blood vessel, right? Here's your blood vessel. As the amount of salt goes up in your blood, it makes your blood more hypertonic. So what else goes up? Water. More salt, more water, higher blood volume, which means your heart has to work harder, and it's higher blood pressure. Okay? So, if your blood pressure is too high, do you want to pee more or less, and why? Tell your bio buddy. Yeah. So if my blood pressure is too high, do I want to pee more or less? More. And why do I want to pee more? Get the water out. Less water in my blood means my heart can work. Yeah, it doesn't have to work as hard. It'll lower my blood pressure. That's why some people take diuretics who have high blood pressure. Okay, because that makes them pee more, which keeps their blood pressure lower. All right, now, when you look at a, go to maintenance of water-salt balance. Because if there are more salts in the blood, there will be more water in the blood, which means greater blood volume, which means greater blood pressure. Okay, so finish that part out. There's a picture. Here's another picture for you. Look at that. Osmolarity. Look at that. That's super fun. Okay? So you have reabsorption of salt, 67% at the proximal convoluted tubule. Establishment of a salt gradient allows water to be absorbed passively. Reabsorption of water, more or less dependent on the needs of the body. The needs of the body to maintain homeostasis. More or less dependent on the needs of the body to maintain homeostasis. Now, Where is the bulk of the water reabsorbed out in the nephron? Proximal convoluted tubule. And why do you say that? I 100% agree with you. 67% of the salt is pumped out, so 67% of the water gets recovered. Okay, so you're almost looking at 70% by the time you're at the bottom of the distal, yeah. Well, no, actually, what I was going to say, descending loop of the nephron. You're already already at 70%. And it gets there's very little, you're still reabsorbing, but right here, this collecting duct, this is critical. You know, and sometimes when you pee a lot and sometimes you pee a little, right? Okay, and that's dependent on, usually, it could be due to what you're drinking, right? Okay, but it could have to do with how much fluid you have had, just straight up water. When you pee, if your urine is dark, 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 okay, what does that mean? What does that mean? You need to drink more water, yeah. Because there's not a lot of water you're peeing out. And think about this, if you pee into a toilet, which most of you would do, okay? But when you pee into a toilet, that toilet is already filled with what? Water. You're already diluting it in the toilet. And if it's dark in the toilet with all the toilet water, then it must really be dark. If you peed into like a glass, okay, or whatever, something, right? Think about how dark it would be, right? That should terrify you, okay? So how dark and light your urine is often determined just by the very last instep. And there's lots of things we're going to look at that control this, but this right here is a big one. It's anti-diuretic hormone, ADH. In your brain, you have your hypothalamus that sits below your thalamus, right? And below your hypothalamus is your pituitary gland. Pituitary gland is known as the master gland. There's two lobes to it, posterior pituitary and the anterior pituitary. Posterior pituitary secretes two categories of hormones. One is called oxytocin, and we're going to learn about that later. That has to do with pushing a baby out and milk coming out of your breastises, okay? And we'll talk more. Well, anyway, and the other one is ADH that comes out of your posterior pituitary. Anti-diuretic hormone. Sounds like I don't want to what? Die. Okay, good. No, but that's good. Anti-di. Listen. Make it make sense to you so you don't have any memorization going on here. Anti-diuretic. Why might I die? Because I lost too much water. So anti-di, I want to reabsorb the water. So what happens is when you have more anti-diuretic hormone, it makes the collecting duct leaky so that more of the water gets recovered. Anti-diuretic. I don't want to die, so make the collecting duct leaky. I'll reabsorb more water. A diuretic, like caffeine and alcohol, think about that. Diuretic, I'm going to pee more, okay, as a result of that. And so it increases. So when you are very dehydrated, you are hoping that your pituitary gland will secrete even more antidiuretic, so you'll keep more of that water in your body so you can maintain homeostasis. Then speaking of the color of pee.
You produce between 2 to 3 pints of urine every day, but most of us still pay little attention to our liquid waste. So what does your pee say about you? And could it be a clear indicator of your body's overall health? Before you pee, the kidneys filter water-soluble waste by absorbing the nutrients it needs to keep, like sugar, back into your body and getting rid of the things your body doesn't want, like toxins. The liquid waste then flows to your bladder, where it's stored until eventually being peed out. If your urine is brown, it could be from eating a lot of rhubarb, fava beans, or aloe. It's also a side effect of some medications such as laxatives, muscle relaxants, and antibiotics. More seriously, it can be a sign of liver disorder or kidney disease. If you're seeing purple, you may be suffering from a rare inherited disorder known as porphyria. Porphyrias cause your body to be deficient in the enzymes which produce heme, an essential part of red blood cells. Green urine, it could be from a new medication or vitamin. Some green food dyes don't get absorbed by your body and can be excreted in your urine, so a green stream is not always something to be alarmed about. especially after St. Patrick's Day. If your urine is blue, you likely have familial hypercalcemia, an inherited disorder found in children which is caused by excess calcium in the blood, also known as blue diaper syndrome. Some medications have methylene blue in them, which can also cause urine to turn blue or green. If it's pink or red, there may be blood in your urine. This can be due to a variety of conditions, from an enlarged prostate, bladder cancer, or even chronic lead poisoning. But red urine can also be caused by different types of medications or from eating richly colored foods like beets and blackberries. In fact, beeturia is the technical term for peeing pink after eating too many beets. If your urine is orange, it could be from eating excessive amounts of food containing high levels of vitamin C or carotene, such as carrots. It's also caused by drugs like a painkiller called pyridium, given to people with urinary tract infections, which turns urine bright orange. Now, normally urine should be a shade of yellow, and it gets this yellow color from the pigment of urobilin, which is a product of the breakdown of heme, an essential part of your blood. Depending on how much water you have in your body, your urine will either be diluted or concentrated with urobilin. Honey-colored, it means your body has reabsorbed a lot of water to keep you hydrated, so now there's a higher concentration of urobilin in your urine, making your pee appear amber-colored. You should probably drink some water right now. If it's dark yellow, this is normal, but there's still more urobilin, so you'll want to drink water soon. No color at all means you've been drinking a lot of water. It could also mean you have consumed caffeine or alcohol, which inhibits the ability for your body to reabsorb liquid in the kidney, meaning you pee out way more water. If you're looking at transparent yellow, you're normal and healthily hydrated. Got a burning question you want to answer? Ask it in the comments or on Facebook and Twitter. And if you want the inside scoop on upcoming episode ideas and behind the scenes, check out our personal Instagram and Twitter handles. And subscribe for more weekly science videos.
Okay. All right. So, the next thing on there, ADH. Could I please have Blue tell about ADH? It's in your notes right there. All right, and then diuretics increase the flow of urine. More water is urinated out. And examples of diuretics are alcohol, caffeine, and drugs that can help with high blood pressure. All right, now tell me, how do gases travel in the blood? Just a little review. Okay, they move by diffusion, but how do the gases actually travel? What are the two gases I'm concerned about? Oxygen and carbon dioxide. How does oxygen travel primarily? On hemoglobin. Perfect. How does carbon dioxide travel primarily? Bicarbonate. How does it form bicarbonate? CO2 and water forms carbonic acid, which breaks down into carbonate and hydrogen ions. Perfect. Does our pH matter of our blood? Yes. Tell me, what can happen if my blood has a low pH? What will I start doing? I'll breathing what? More or less? More. Will my heartbeat beat more or less? More. I'm trying to get more oxygen to counteract probably the loss of oxygen because I'm producing so much what? CO2. Who does that here in my brain? Medulla oblongata. Depending on how much carbonic acid or bicarbonate you have, that can also help regulate my blood pH, right? And the kidneys help with it too. Whose turn is it, young or old? Old? Explain what's going on in this picture. I know you can do it, old one. Are you starting to feel smart? Look at all that stuff you tell me. Oh, blood, kidneys, I got it. That's right, crazy smart, Mom. Crazy smart. All right. So go to maintenance of acid-base balance. Normal pH of urine is around 6. I have little pH papers. If you ever want to check your urine pH, you can. Our blood is around 7.4. And we can do that by excreting hydrogen ions or absorbing bicarbonate ions. So what are the three systems that help with us maintaining our pH of our blood? A is the acid-base buffer system, which you just reviewed for me, the bicarbonate, carbonic acid concentrations in the blood. Second place is our respiratory center, which you know as the medulla oblongata. And then the third is the kidneys. It is slower acting, but more powerful. Slower acting, but more powerful than the two above. Because it can specifically get rid of or reabsorb hydrogen and bicarbonate. Slower acting, but more powerful, because it works on the numbers themselves. How many hydrogen ions, how many bicarbonate ions you have. Okay, so now I want to jump back to this. Have we talked about metabolic waste?
Yes.
Have we talked about water-salt balance?
Yes.
Have we talked about acid-base? Yes, so where are we at? Hormones. If you asked somebody, though, who didn't have a biology class recently, mostly they would say your kidneys are about getting rid of what? Waste. They wouldn't think about all these other critical functions that help to maintain homeostasis. Okay? And the next one's going to be pretty important too, these hormones. So let's talk about that. And for a minute, could you please put your computers at half mast, kind of folded down towards you just for a minute and get your eyes up here? Because I'm going to take you down a bunny hole. And I want you'll get it, no problem, once I've kind of taken you through it. Okay, so focus just for a minute. Okay? So, when you have low blood pressure, okay, when you have low blood pressure, aldosterone is secreted from the gland above your kidneys. What's the name of that gland? Adrenal gland. When we think of the adrenal gland, what do you think most people are going to think of right away when you think of adrenal gland? Adrenaline and noradrenaline. Perfect. And that's fight or flight. Good. And adrenaline and noradrenaline come out of the center of the adrenal gland, and that's referred to as the adrenal medulla. Okay? But there's an outer part to the adrenal gland, and that's called, and it's the same thing as the kidney and same thing as your brain. The outer part is called the adrenal cortex. Okay? The adrenal medulla and the adrenal cortex secrete different things. Okay? The adrenal cortex, one of the things it can secrete, it's a mineral corticoid known as aldosterone. Okay, there's an umbrella of mineral corticoids. One of those, primary one, aldosterone. What aldosterone does a couple of things, but right now we're going to focus on aldosterone. Makes you reabsorb more sodium out of your nephron. Who's going to follow the sodium? Who's sodium's partner?
Water.
Chlorine, right? So you form like salt, right? And then who's going to follow? Water. Exactly. So how does the adrenal gland know to tell the kidney via aldosterone, hey, reabsorb more water? So that's what we're looking for next. Why does this happen? How is aldosterone triggered? Okay, here's aldosterone still. Okay, same slide, backing out just a little bit. When you look at the nephron, when your blood is coming in at your afferent arterial, if the blood pressure is low, then your kidney starts to secrete something called renin. Okay? So, why would that be important? If your blood pressure is too low, how could that be detrimental to your kidney if the blood pressure is too low? Yes. Or, no, I mean, like, what is one of the kidney's jobs? Is to do what? What happens what comes after the afferent arterial? Glomerulus. What happens at the glomerulus? Filtration. Now, why do things move out of your blood? There are two pressures. What are the two pressures? Hydrostatic and osmotic. Hydrostatic pushes out. If that hydrostatic pressure is too low, what's going to happen with your kidneys? There's no filtration. Exactly. You'll have less filtration because the blood pressure is too low. Where's the place right before that filtration is going to happen? Afferent arterial. So if the afferent arterial, if the blood pressure is coming in too, could it come in too high as well?
Yeah.
Absolutely. Could that be bad for your kidney?
Yes.
Yeah. In fact, it can damage your kidneys terrible because it can basically rip the glomeruli apart, okay, if the pressure's coming in too fast and furious. Okay, but if it comes too low, kidney can't do its job. It can't do glomerular filtration. So the kidney starts secreting renin. So what does that do? okay? Because we still haven't learned how renin gets aldosterone to get secreted. So now let's go one more, a little bit farther down our rabbit hole. Do you remember how I talked to you about in your stomach, what gets digested in your stomach? Protein. Using what enzyme? Pepsin. But if you remember, we talked about, there was like the riddle, right? How do you store something like pepsin when pepsin digests protein and you're storing it in a protein sac like your stomach? How do you store it as? Pepsinogen, an inactive precursor, right? So your liver makes an inactive precursor called angiotensinogen. And angiotensinogen gets converted to angiotensin 1 if you have renin. Okay, so that's what you're looking at right here. Angiotensinogen getting to angiotensin 1. That will become angiotensin 2, and it's actually increased levels of angiotensin 2, which gets the adrenal cortex to secrete aldosterone to tell the kidneys to reabsorb more sodium so more water follows. So, now, there's only one thing we're missing right here. Angiotensin 1 has got to become angiotensin 2. The thing that does that, you ready for this? The lungs. Your lungs secrete something called ACE. And ACE converts angiotensin 1 into angiotensin 2. So where did it all start? It started right here, right? We had low blood pressure at the afferent arteriole. So the kidney started secreting more renin. Renin made a product from the liver go from an inactive precursor, angiotensinogen, into angiotensin 1. Then something from the lungs got involved to make it go to angiotensin 2. Then that substance talked to the adrenal cortex, told the adrenal cortex to start secreting aldosterone. Aldosterone talked to the kidneys and told the kidneys, hey, reabsorb more sodium because we got to increase our blood pressure. Do you see how many different systems got involved in maintaining your blood pressure? And you know what, oldest bio buddy? Give it a shot. Okay, go. All right, they do okay. Youngest bio buddy, it's now your turn. Youngest bio buddy, here is your turn right here, and I'll make this a little bigger too, so you can see it. Okay, go youngest bio buddy. Okay, now, here is another way to look at it. This should not terrify you in any way, but this shows you all the things that happen. So here's a renin from the kidney. You recognize this, angiotensinogen becoming angiotensin 1. What's between angiotensin 1 and angiotensin 2? ACE. ACE from the lungs, right? Look at all the things it does. Retention of sodium by the kidney via what? Aldosterone, right? So the adrenal cortex is going to secrete aldosterone. Water retention by the kidney, and it's going to say vasopressin. I'll be talking to you about a vasopressin in just a minute. It increases your appetite for salt. If you have more salt, then what?
More water.
More water. And it makes you want to drink more. It actually triggers the drinking mechanism, which will then increase your blood pressure. If you get to the point where you're like, oh, and I know I get this way. Oh my gosh, I'm so thirsty. And it's like you can just chug through water, no problem. That means you're way, under budget here for your water, what you need. Because at that point, all those reactions had to take place to trigger you to go, oh my gosh, I'm so thirsty if I don't drink something now. If your body is telling you and you are feeling compelled to drink, okay, then you have already not had enough water for some time. So that's why it's important to drink a little bit. You need to be heavy drinkers, okay? You need to have a little bit of water all day, you know what I mean, all day long, okay? All day long you need to be drinking water. Now, let's take it a step further. If low blood pressure is bad, what else is going to be bad? Now, I know you can do this, dark-shirted bio buddy. Okay, go for it, dark-shirted one. I know you can figure this out. Go ahead. You know, come back to me. Where is the blood pressure going to be the lowest in your body? That's the speed. Speed will be the slowest at the capillaries, but where's the blood pressure the lowest? No. Blood will only go from higher blood pressure to lower blood pressure. So your lowest blood pressure at all better be entering your heart. Right? Better entering your heart, better be where you have the lowest blood pressure. So blood will always move towards your heart. Okay? Facilitated by valves, right, in your veins, facilitated by skeletal muscles pushing against the collapsible walls of your veins to keep it going in one direction. But blood's always got to move from higher blood pressure to lower blood pressure. So when it dumps into your atria, the pressure ought to be the lowest of all, right? Coming from your vena cavas and coming from your what? Pulmonary veins, right? Dumping into your atria. So there, if it's coming in, okay, and your atria are stretching as a result of it coming in fast and furious, that means your blood pressure is too high. That's a good place to sense it, right? Does that make sense logically? Okay, and now it releases, I have seen ANP, I have seen ANH, and I have also seen it listed as ANF. Okay, so I'm just letting you know that. But this counteracts everything that we just talked about, so that you will then have lower blood pressure so you don't damage your kidneys or any other capillary beds in your body. So putting it all together, I made a little collage for you, okay, which may be terrifying. I'm not meaning it to be, okay? But let's take a look. The one you just learned about, ANH, look what it does. If there's high blood pressure, the red line is meant to inhibit. So one of the things that you can see it inhibiting, red, is going over here to what? ADH. Okay? So it's inhibiting anti-diuretic hormone that's coming from your posterior pituitary. Because it wants you, if your blood pressure is too high, it doesn't want anti-diuretic. It would almost want a diuretic. You pee what? More. So it inhibits ADH. Another thing it inhibits is right here at the beginning of the whole thing. Who? Renin. So angiotensinogen just stays angiotensinogen. Right? So just go right to the source. Right here. Then if you look at what else happens, you have something else. You have, remember the vasopressin I talked to you about? So you have something called ACTH, which means adrenal corticotropic hormone. You're going to be learning these hormone names. That's one of our, chapters that we need to know. Okay? Adrenal corticotropic hormone, what are you hearing there? Adrenal cortex. It affects your adrenal cortex. Okay? And it comes from your anterior pituitary, and this would stimulate then aldosterone release. It's stimulating that. Okay? And then you recognize these. You can see renin, you can see angiotensin 2, and you know the steps that have to take place in there because we already learned those. So that kind of puts it all together. So look what's helping to regulate our blood pressure. We've got our heart, right? We've got our kidneys, we've got our liver, we've got our pituitary gland, and what's not shown there are your lungs, right? All of those are helping to maintain homeostasis. Now, who are the overarching systems that control our homeostasis? Nervous and endocrine. Nerve can do things like make sure our capillaries are open or dilated, because that's going to regulate our blood pressure too, right? So we haven't even talked about that aspect of it. But we learned about capillaries. Remember the sphincters on the capillaries? Now you shunt blood. So if your blood pressure is too high, you could open some of those up to spread the blood volume out over a larger area. That would lower your blood pressure, right? And then look at all these different hormonal interactions we just looked at. You've already learned a bunch now. You've talked about renin, aldosterone, ADH, ACDH. You've talked about ANH. These are all different hormones that are going to help regulate your blood pressure as well. Okay, good. Now, on your notes, go to where it says secretion of hormones. Little letter A, renin from the kidneys triggers the adrenal cortex to secrete aldosterone, which increases the absorption of salt. And you and your bio buddy look through 1 through 4. I know you can fill in those 2 missing words without me because you know it. What'd you put in the first one? Liver. Good. What'd you put in the second one? Lungs. Good. Okay, we got another one as well, EPO. Look at this. So blood volume, blood pressure, this is going to be important to kidney function, but look what else the kidneys do. Secreted from our kidneys is something called EPO. EPO stimulates the production and maturation of red blood cells from our bone marrow. So the kidneys also talk to our bone marrow and get our bone marrow to generate more red blood cells and to mature them. This has been made artificially by a company down the street, Amgen. Yeah, to help people recovering from chemotherapy. Can you think of a reason why somebody would want to take this drug for another reason, illegally? What? I can't hear you. Doping, yes. And because if you were an athlete and you had some form of EPO, then you would generate more red blood cells, which means you would carry more oxygen and experience less fatigue. And a lot of times when they test for, I am not current on all drug testing, so I don't know. But a lot of times what they're testing for is not even the EPO anymore because somebody's going to take something to mask it. So they test for the masking drug. Do you see that? And then they know, oh, you're probably trying to cover that up. Okay, so that is yet another one. So EPO stimulates red blood cell production. And then also your kidneys help activate vitamin D. And by having vitamin D, you have better calcium absorption. So here's a vitamin and vitamins are often coenzymes, right? Remember how we talked about that? Cofactors. Okay? And then calcium. What do we need calcium for? Think about it. In your bones, right? Connect all the lines there.
And it's in like the synapse.
Yes. At the synapse of all your neurons, calcium's really important. Yeah. Remember at the presynaptic neuron, instead of sodium coming in, calcium comes in, presynaptic vesicles fuse. You putting it all together? Okay. So when we talk about the kidney and we talk about its role, I want you to see what a critical place it plays in our homeostasis. And when we talk about the nephron, yeah, we're talking about how we recover water and all of that, but there's so much more to that picture, and that's what I want you to see. So the last one is help vitamin D, which you can say helps with calcium reabsorption. And I think I have one last question on this, my super smarties. See how difficult it is to talk about your systems in isolation?
It's easier to do it.
It is. know, I like doing this. The only bummer is with this new system, you can't see the questions. Like, if you're watching this at home, you don't see it till the answer comes up. Right? Because you can't see the question till I hit start. Yeah.
That's fair. So Mike.
Yeah, it makes Michael not win every time, potentially. But
You never know.
you never know. Oh, great sadness, great sadness. Only 7 of you are champions. Show your screen right now to your bio buddy. You're going to need to talk about this. Okay? Think about it. The presence of ADH, anti-diuretic hormone. If I don't want to die, I better recover water. Yeah. So, causes an individual to excrete less water. To excrete. I didn't say to absorb, I said to excrete. Okay? Got that? Discuss with BioBuddy. If you missed it, why? Okay? I didn't read the answer. All right. The end. Good job. All right, get out your chapter 37 group shared notes. Hopefully that was helpful. Go have a glass of water.